All right, taking a look at 811 application to physics and engineering. We're going to look at moments and center of mass. The overall objective is to find the point P on which a plate of any given shape balances horizontally. The point P is called the center of mass, or center of gravity, of the plate. We are going to discuss the center of mass for n particles in a one-dimensional system. We're going to look at n particles in the xy plane and a flat plate or lamina with uniform density. We're going to have a new letter here, Greek letter here called rho, which occupies a region of the plate. So let's consider a seesaw. We'll balance if your mass of the first person here to the left times the distance away from the fulcrum is equal to the mass of the second person times the second distance. We call this multiplication of the mass times the distance is our moment of m sub 1. And over here, this will be our moment of m sub 2, or mass 2. So if we said mass 1 is 20 kilograms, mass 2 is 25 kilograms, to find the moment, we just multiply that to the distance. Let's say we have 2 meters each. So the moment of mass 1 is going to be 40 kilograms per meters, and the moment of mass 2 would be 50 kilograms per meters. So if this is the case, obviously what's going to happen is the seesaw is going to go down on the right, up on the left. We're going to get a clockwise rotation here because our moment at m1 is less than the moment of m2. So we can balance this seesaw with these two individuals here by moving the greater mass closer to the fulcrum. So move this person closer in, we can get back to being balanced. So what we would do is solve for a new distance d sub 2 back here in our balance formula. So we would take 25 times d sub 2 is equal to 40. Divide over the 25, distance 2 would be 1.6 meters. So they need to be 1.6 meters from the fulcrum. Second way of getting this balance is moving the fulcrum closer to the greater mass. The question is, how much closer would we have to do that? Well, finding the center of mass, we're going to call that x bar. To solve for x bar, you need to turn this into a number line and give these distinct values. So as you can see, here would be my fulcrum. We'll call that x bar. That's my center of mass. And now we need to have a value. So my x sub 1, where my mass sub 1 is at, is going to be a number associated to my x-axis, and the same thing over here with x sub 2 and m sub 2. My distance then from mass 1 to the center of gravity, here's my d1, would be x bar minus x sub 1, and for distance 2 would be x sub 2 minus x bar. So if we take our formula that we had for when we're balanced and put in these values, so x bar minus x sub 1 and x2 minus x bar for d sub 2, multiply it all out, and to solve for x bar, get these both on the same side. So I'm going to add this term from right to left, and I'm going to add this term, since there's no x bar, from left to right. And that gives me this new equation. I can factor out the x bar as the GCF, divide this binomial over to the other side, and it doesn't matter which order you put them in, whether it's m2 times x sub 2 plus m sub 1 times x sub 1, doesn't matter. Either one of those are fine. So now we can answer that question, how much closer? So to convert it into a number line, what I opted to do was to put my fulcrum at 0 on my x-axis. To the left, person 1 would be at -2, person right over here would be at 2. So let's go ahead and solve for x bar. So now we have 20 times -2 plus 25 times +2 all over 20 plus 25, which will be a 45 on the bottom. So -40 plus 50 is going to be a 10 over 45, which reduces to 2/9. So we would need to move my red fulcrum triangle here 2/9 meters closer to the right. And now it would be balanced. All right, number one, extending to n particles. So now to add more people, if you will, to the seesaw. With masses m sub 1, m sub 2, m sub all the way out to m sub n, located at x sub 1, x sub 2, all the way out to x sub n, moment of a system about the origin is the measure of the tendency to rotate about the origin. So m sub o, the moment about the origin, which can also be known as capital M, they're interchangeable. You need to take the mass of the first particle times its location and do that all the way out to m sub n and x sub n. We'll add that all up. So that would be your summation from I equals 1 to n of m sub I times x sub I. If your moment about the origin is equal to 0, we'll be balanced. All right, we will be in equilibrium. Come on, mouse, what's the problem? There we go. All right, so that means what we want to do is take mass 1 and go x sub 1 minus x bar plus m sub 2 times x2 minus x bar and have that all equal to 0. So again, my summation from 1 to n, we just switch up the notation. So now again, we're looking for the distances. So x sub I minus x bar is going to be the distance. So we want to multiply those out, add them all together to see if it's equal to 0. So to solve this for x bar, we'll go ahead and write two summations here. We're going to add this one over to the right. I'm going to factor out my x bar to the front of my sigma notation because it does not have an I attached to it. There it is. I just moved them around. I like to solve from left to right and then divide this over to my other summation. So this is going to be my x bar if I'm not equal to 0. And then I can find my center of mass. So top, that's my m. Bottom is the sum of my masses. So x bar will be at the moment about the origin divided by the total mass. That's how I find my x bar if my moment about the origin is not equal to 0. All right. So m is equal to m times x bar. Just a little side note from this new formula here. You can multiply the total mass to x bar, and that would equal the same as the mass. Or excuse me, that mass moment about the origin. So let's look at an example. And again, we don't have to do lots of points here because I think once you understand a couple points, you'll understand it for if there was dozens of points. So let's say we had a particle at -3 and its mass was 7. We had another particle at -2 with a mass of 4. Our third particle is at 4 with a mass of 4, and let's say we have one at 5 with a mass of 3. So my moment about the origin is 7 times the -3, the 4 times the -2, the 4 times the 4, and the 3 times the 5. Crunch the numbers, we get 2. So therefore, we are not balanced. We are not in equilibrium. So to find that x bar, we're going to take our moment about the origin, the 2, and divide it by the total mass. So we need to add up all of our masses, 7 plus 4 plus 4 plus 3. That's 2 over 18 or 1 over 9. So right there would be my center of mass. So again, if you were thinking of, a teeter-totter again, this is where my fulcrum would have to be, is if we had two people here with this mass weight and these two people over here with that mass weight.